Hey there, brilliant minds and binary buffs! Before we dive into today's digital deep dive on conquering the JavaScript interview, let's illuminate a path for continuous growth. With Covalence's community membership, which you can find a link for in the description down below, you're not just getting over 300 hours of cutting edge coding content, full stack programs, and our comprehensive React course for just $25 a month, you're joining a vibrant community where learning never goes into standby mode. Any new updates to our courses, they're yours for free, so stay current, stay connected, and stay coding with Covalence. But now we're going to gear up and explore the nitty gritty of bit manipulation in my little mini series here. Bitwise Basics, as I think is what I ended up calling it. I don't know. I'll make up a new title for everyone if I feel like it. Who's going to stop me? Y'all? Well, maybe you could if your comments are loud enough. We'll see. But we're going to go with a classic puzzle on this one called Finding the Hamming, H-A-M-M, Hamming weight, or sometimes called the population count of an integer. Now, those names by themselves also meant nothing to me when I first learned them, so I'll go into a bit more detail of what our problem is going to be here as you read along. Remember, you can grab this prompt and the code solution from the CodePen. I do advise that even if the code is ludicrously simple to write, which again, the deception to these bitwise operators as we learn them is surprised they are fairly easy to write, it's still worthwhile for you to code along with me and write it even if you have no clue what's going on, because it will help you build that muscle memory. You'll build that connection in your brain for the next time you actually have to write it by yourself rather than just copy and paste it. So buckle up as we count set bits and uncover the power of bitwise wizardry in JavaScript. So here is our problem: counting set bits. It's commonly referred to as the Hamming weight, or sometimes population count, as my intro and this little bit here, pun intended, is showing you, right? It's very simple when you understand what it is. It's simply determining the number of ones, which are called set bits, in the binary representation of an integer. In other words, it's just counting about how many bits in a number are on the one setting, aka the set bit. So if we imagine a number like 11, I think is represented as 1101, then right here, yeah, so let's take a look at this one for example. The binary representation of 5 is 101, and in those 3 bits, we see 2 that are on or set to 1, aka it has a set bit count of 2. That would be our output, right? So that's what we're looking to do here. And like I said, it's not that difficult when you understand what it is. So if you're wondering why is it called Hamming weight, that's because it was named after Richard Hamming, an American mathematician and computer scientist. Hamming introduced several concepts in the field of information theory and coding, one of which is the Hamming distance. It's a distance between two strings of equal length is the number of positions at which the corresponding symbols are different. In the context of binary numbers, the Hamming distance is influenced by the number of set bits, which leads to the concept of Hamming weight, right? So the Hamming weight of a binary number is the number of symbols that are different from the 0 symbol of the alphabet used. In the binary, it's the count of ones, basically, right? So, and the term population count, it's straightforward. It doesn't really have a history that I could find behind it. It just refers to counting the population of set bits, and that's all it really is. And I like that one better. So Hamming, in case you come across it, then you can automatically begin thinking of today's little algorithm and how we're going to solve it using bit manipulation. And I'll even show you the way you would do it without it. As always in JavaScript, there's a number of different ways to do things. But the whole point today is to try and solve this problem just using bitwise operators and discussing why they are so cool. And as always, I've made some diagrams that I'll have uploaded to Imgur, as well as links in the description down below if you want to pull them up as we talk about them, as I'll also showcase them here. So like I said, you plug in some numbers, that number needs to get converted to binary, and that converted binary number is going to have a bunch of zeros and ones, and our goal is to simply count the number of ones and output that. So it's pretty straightforward after you break down what it actually is, despite those fancy names, Hamming weight and population count. It's simple. Count some ones in a list of zeros and ones. So we have our function. Its sole parameter is going to be an integer number n. We're not going to worry about very, very large integers, and we're not going to worry about positive or negative numbers, as that could affect the output or what the code's going to be, depending on what we're what our input's going to be, that would make it a slightly bit more complicated, and there are some easy workarounds to those things that aren't too bad. But we're going to focus on just simple. Let's just imagine we're going to get simple positive integer number inputs, and that's all we're going to get. So to solve this, we're going to be using two new operators. Remember, in the previous video, which I'll try and remember to have in the description down below, if you just look at I know every time I write the description, there is a playlist link to this, and you can start at this video and go back one video in the playlist, and you will see the last video, which we use the XOR operator, which is like that. And in this video, we're going to be using two new ones called the AND operator. I knew where it was on the keyboard. You saw me looking at my keyboard there. We'll fix that in post. We'll make it look like I know what I'm doing. And then we're also going to do one called the right shift. So we're going to do right shift, which is done by that right there. And right shift can receive a number afterwards, so it can be like 1 or 2. You can actually shift by several points. So these are going to be the two bitwise operators in today's coding solution. So in order to count this, we need to convert it to binary, which remember, bit manipulation and these bitwise operators can just do that for us without having to do anything fancy. So all I'm going to do is we need to count the number of ones that appear in a binary number and simply return that. So this is going to be as easy as starting up a count variable, initializing it with the value of 0. At the end of this function, no matter what we do, we're going to have to return that count no matter what solution we take here. And what we're going to do is very straightforward. Now, because we don't know how many iterations we're going to have to do compared to a for loop, we're going to use a while loop in this case. We're going to be using our number value n, which will be converting to a binary value using bitwise operators here in just a moment. And here's what we're going to do. We are simply going to count using the ampersand. So we're going to say plus equals. We're going to increment the count variable by how many ones we count. And only if that binary value we're currently looking at, right, this little binary integer we're looking at here in representation, if that bit we're looking at is a 1, and we use this AND bitwise operator logic, which I'll just talk about in the diagram here in just a moment, if those both are a 1, it will be incremented by 1. If the n value of the bit is 0, it will result in a value of 0 and increment by 0, aka it won't. So this is a clever trick to only count the ones that appear and ignore, or rather zero out, all the zeros to make sure they don't falsely increment our count. So again, the count is the length of ones we have found, and this AND trick, this bitwise operator AND, is a nifty way to count that. So then we simply have to continue down the line of all of our bits until we're out. And that is actually done very simply with this little command right here, because we have to reassign it. Because remember, this is a reassign, so this is technically that right there is what we're looking at in terms of shorthand. So all this does is it shifts all the bits to the right by 1. So surprise, surprise, there's that operator, the right shift. This is how many spaces you want to shift over. You can do more than 1 if you want to, but that's it. We're simply going to say, hey, the n value, the binary value integer we're looking at, shift all the bits over to the right by 1, add something new at the beginning, which we'll talk about here in a moment, and that's it. Shift it on all over. So that's all it does. So shift all the bits over, see if that's a 0 or 1 and count it. If it is, if it's a 1, count it. Otherwise, count a 0. That's it. Shift all the bits to the right, count it again, shift to the right, count it, shift to the right. Eventually it zeroes out, that becomes false, and then it stops the loop, and then it returns the count. And voila. That is it in terms of code. So once again, it's like, yo, what? How is that possible? Let's see if it works. Let's count set bits of 5. Console log. Count is count. Invoke it. Count is 2. Is that what we're expecting to see? Yes, the binary representation of 5 is 101, which has 2 ones, so it returns a count of 2 to us. Let's do a 7 and a 10 now. 7, 10, let's do this here. So 7 is 111, meaning we expect a count of 3. Remember, the binary of 7 is 111, and the binary of 10 is 10, 10, 10, like that, right? So we expect to see a count of 3 for the 7, and then a count of 2 for the 10, and we get 2, 3, 2, right? And that is exactly what we expect to see, and that's what we get. So the job is done. We have done a successful population count with very minimal code in terms of what we've had to write here with our bitwise operators. So I'll show y'all the other way to solve this without, if you didn't know how to do this, like let's say, for example, you were in an interview and you were like, well, first off, how do I convert a number to binary? It's actually pretty straightforward. But this is a simple and cool way to do it. And like I said in the previous video, if you are throwing out bitwise operators to solve problems in JavaScript interviews, and you can explain how it works and why it works this way, maybe even its pros, cons, limitations, etc., you will be so extraordinarily cool. And honestly, that's the whole point about it. We had a discussion the other night in our Discord channel saying that I was deep diving these because I find them fascinating, and I think they are, honestly, you feel cool just doing them, and that's the most important part. Secondly, they're very efficient, and again, it demonstrates you have a very strong fundamental understanding of not just JavaScript code, but even lower level language like binary, which I think is pretty cool. Okay, so more importantly, like I said in previous videos, I'm trying to get to code faster and explain later. That way you'll actually have something to look at on the screen and not just at my face in the corner talking. So what is so cool about these, right? Well, first off, as a reminder, I'm going to probably say this in all the videos because these are new to a lot of people probably stumbling upon this. Bitwise operators are functions that operate on binary integers at the level of their individual bits, aka the zeros and ones. Each one has a specific job. We have the and ampersand operator. We have the right shift. As you can imagine, there's also a left shift operator, which looks like that. Also can take a number after for how many bits to shift to the left. We talked about in the previous video the exclusive OR, aka the XOR operator, but we also have the OR single pipe operator. And we also have the not, which is the tilde right there operator. So we have a couple of bitwise operators, and again, I'm going to try and cover all of them in this little video series and then combine them all and use them in different ways. Each one takes binary data and morphs it in a unique way following rules of binary arithmetic. So in plain English, imagine you got a string of Christmas lights. Each bulb is a bit. Bitwise operators are like the switches you use to control which lights are on and which lights are off. Combine switches with and, light up more than a single switch with or, flip all the lights, not, or even make unique lights only on like XOR. Or you can shift the whole string to the left or to the right with the shift operators. As the name implies, they're pretty straightforward. So let's take a look at our two operators that we've dealt with today in diagram form. Again, I should have these available on a link in the description that you can pull up on Imgur and you can save, or probably just maybe I'll make an album when I'm done of all these, so you can kind of use them as flashcards. That way you can remember what they do. So the AND bitwise operator is a single ampersand, not to be confused with the double ampersand for the logical AND. Right? This is not logic. This is bit manipulation here. My cat Percy is right in front of the monitor, so I can't read. Come here, buddy. You want to say hi to the camera? No? He's in my thumbnail. I might as well put him up here. Say hi, Percy. He says hi. Okay, so bitwise takes two binary digits and gives back a 1 only if both are 1. If either or both are 0, it gives back a 0. That's all it does. It's very, very straightforward. So I like how I started with one of the most difficult ones with XOR in a previous video, and now it's going to be on the downhill. So if you got the last video, this one will be no problem. Piece of cake, right? Super easy. Barely an inconvenience. So think of bitwise AND as a security guard at a club. You got two friends that show up to the club, Bit and Byte. They both show their IDs. The guard only lets them through, result being 1, if both Bit and Byte have VIP passes, aka their bits are both 1. Otherwise, if one or the other doesn't have a binary or a VIP pass, or neither have a pass, then there's no entry, which is represented by a 0. The examples here are as follows. Again, Bit and Byte neither have a pass, then 0. That means no entry. If Bit doesn't have one and Byte has one, so the two friends, 0 and 1, still a no-go. They both got to have one for this to pass. If you reverse the operation and Bit's like, well, Byte doesn't have one, but I got one, still doesn't matter because one and or the other is a 0, aka doesn't have a pass. But if they both got a pass, then they can get in and the guard lets them through, which is our output of 1. So again, if they're basically, you can think of it as if there's a 0 anywhere in the comparison of the two bits, then it's going to wind up as a 0. It annihilates that way, which is actually a property term for AND. But if you see two ones or a number ANDed with itself, it's always going to return that number back to you. Or in this case, when we're looking at the number 1, aka like one little bit, it's always going to be a 1. But a number ANDed with itself is always the same thing. Typically, you'll see this diagram as follows. Remember, the other XOR had like the line, the extra line, and the indentation on the butt end of the gate here. This is more like computer science, electronic, like, electric stuff here, and then circuitry. But nevertheless, I think it's good to know what it looks like. That way, if you encounter it in the wild, you'll know what's being shown to you. If A and B pass the test, and they are combined as A and B after the diagram output here. So that's what the ampersand bitwise operator is for us here. Now, the other one we use in today's solution is the shift right operator, right? Get it, right? So, right shift, aka the two less than signs put together, the two gang signs put together right there, pushes all bits in a binary number to the right by a certain number of places. Remember, in my code, everything got pushed over by 1. That is why I included the 1 right there. Okay? Now, specify by the second operand, which was, the number 1 I've highlighted right here. Filling in from left with the sign bit for signed numbers or 0 for unsigned. So there are two different ways to reference these double less than signs right here. You can actually include a third here, which is called unsigned integers, meaning it doesn't care if it's positive or negative. It always fills in with zeros. This is for signed integers, meaning this will fill in either ones or zeros when we're shifting, depending on the sign of the integer, whether it's negative or positive. So that's why I said we're not going to worry about that, but I want you all to be aware of it. So triple is unsigned, meaning you always fill in with zeros, no matter positive or negative. Double is signed, meaning it's going to look for the numbers negative or positive, and that will fill in with ones for negative, I believe, and zeros for positive. So yeah, that's what's going to happen. So in this case, imagine bit and byte are on a conveyor belt with a series of boxes to the right. Every time the right shift button is pressed, they both hop one box to the right. Bit being on the edge falls off into the void and explodes, while a new box with either a copy of byte if signed or an empty box if unsigned enters from the left. So that analogy is all right, but I think this one's actually very easy to understand just by looking at it. So let's say we start with this number right here, 10110. That is the number we're looking at. And if we say bit shift it all to the right 1, what did I just say? That sounded wrong or bad. Bit shift, there we go. I gotta be careful saying that one fast. Okay, so bit shift everything to the right by 1. So basically, this 0 falls off into the void and explodes. So we wind up with 1, 1, 0, 1, and then because we're doing a positive integer, it fills in with a 0 up front right there. And that's what happens. So that's why we get 0, 1, 0, 1, 1, and the final 0 has fallen off the cliff. Now, what if this is where we can provide that operand and increase it to say, hey, shift right by 2 bits. Now, this shift right is not from the original input, but rather what we're looking at right here. So think of the second line as our new result, and I want to take this result and shift it to the right twice. So that's why these two will then fall off a cliff and explode. 0 becomes our leading number, then the 1, then the 0, and then the 2 zeros at the beginning get filled in because we move by 2 bits over. So that's what happens there. And the diagram, there really isn't like a gate style diagram like you see for the other bitwise operators, but basically you'll always see like your number, your binary representation of your number in like these squared out boxes right here. And all you have to do is take the thing on the furthest to the right on a shift right, blow it up. It's gone. It's fallen into the void and it's nuked permanently. Then you take everything else and shift it to the right 1 space. And at the beginning, depending on how many and what your integer and whether you're doing signed or unsigned, you fill in with either zeros or ones. Start with zeros until you understand the difference. I'll probably go into that in a separate video. I want to keep it simple for here. But yeah, that's all it does right here. So it just shifts everything to the right 1 and fills in on the furthest thing to the left with something new. That's all it does. So yeah, that is how this thing pieced together does this job. Now, things to remember about the bitwise AND operator. It's idempotent is a property term to know for it. Idempotent. There we go. Any number bitwise ANDing a number with itself doesn't change its value. So that's all that means there. So like there's bitwise ANDing a number with itself can never change its value. It's going to be the same no matter what. The same is the opposite is true as if anything was 0. If you bitwise and any number with 0, it gets annihilated because it becomes 0. It's a 0 property. It gets blown up. It's commutative, so commutative, the same thing like our XOR, meaning A and B is the same as B and A. It doesn't matter in which order you do them in. It will be the exact same output each time. So it doesn't matter which way you do it here. And for example, if we had an AND C now added on to this mess here, it really wouldn't matter if you did it this way, meaning you're like, oh, I can make this behave strangely by doing the following. And you would be wrong. This is called an associative property of the bitwise AND operator, in that it doesn't matter. The order of stuff does not matter. It will be the exact same thing every single time. So you can't change the response or output by trying to group random operations of it with parentheses or things like that. It won't matter whatsoever. Those are the important things to know about the bitwise AND operator. Right shift is a little bit more complex than that when it comes to its properties. Because you are shifting things over, it's not idempotent, meaning every single time we apply a bit shift to the right, the number will continue to shift until all the bits are all zeros or all ones if it's negative numbers, right? So you are changing the value of that number every single time you shift those bits on over. It also preserves signs, right? So for signed integers, for unsigned, doesn't care, always starts with zeros. This will care. Positives are zeros, negatives will fill in with ones instead. So that's what you have to remember there. And it is non-commutative, meaning the order and number matters, because remember, you are changing the value as you shift stuff. So changing the order of stuff will make it so that the output will be different based on its order. So you can't just say, I know this doesn't matter which way it's written. On shifting, got to remember the order and grouping is important, unlike the rest of them. So yeah, that's just the basics I wanted to cover on the AND bitwise and the right shift bitwise to achieve this right here. So in terms of big O in this particular case, it has a time big O complexity of log n. That's because, as we can see here, this thing will always loop over a number's bits at least one time, right? So each iteration removes, right, the least significant bit of n by shifting it to the right, which means the loop runs for each bit of n. So the bigger n is, the more times this thing will have to keep running its loop. Now, because the number n isn't directly proportional to the amount of iterations, because again, we are not thinking of the number itself as what we're iterating over. We are iterating over the base 2 or binary version of that number. So basically, it has to convert from an integer to its binary representation and loop over it that many times, which is actually log n, right? So it's just some math, so you can remember that, hey, how many times of an input number converted to binary will a loop have to run over it? Log n times, basically, about that. So that's why we consider that about log n for its time complexity. And the brilliant part is that it has a space complexity of big O of 1, because just like in our previous XOR solution video, the space used by the algorithm is constant. We assign this variable and it increments a fixed number. It only uses a fixed number of variables, increments, regardless of how big the input is. This thing will just grow in its space, and that's it. There's no weird object map or nested loop or anything like that, or array that's growing in size as well as we go through this. Now, I mentioned this is solvable without the bitwise operators, but it's a little bit less fun and cool to look at, but I figure I might as well show y'all anyway. Let's call cool solution. So we'll call it function set bits non-bitwise, so we're not going to have a non-bitwise solution here. We need to convert it to a binary string, so we're going to say binary string equals the input value number n dot toString, and if you provide a 2, that's what converts it to binary. So let's go ahead and do that so I can show you how it works. We're going to call setBits non-bitwise 5, which was 101. So as you can see here, the .toString function, and we provide a base of 2 into the parameter of toString, which you don't do all that often unless you're messing with this. This converts that number into a binary string. Now that I got a string, you guessed it, I can now split this string around empty space. Now we have an array of string values of zeros and ones, and what I can do is I can filter the array out of all zeros. So I can say for each bit in the array, I now want to only filter the bits that have a string value. Remember, that's important. String value of 1. We have now filtered out all the zeros. I have an array, which means I can then tell the length of the array, which is 2. So that's what you would return in place of this console log. You would return the binary number representation of what's converted, split into an array of their individual bits, filter out the zeros or filter the ones only, and once you have an array of string 1 values, the length of that array is how many bits or set bits are in that binary number. And then all you do is return it, and that is that less cool solution right there. Now, in terms of big O and why the other one is a tad better, this one, its time complexity, I believe, is the same thing. We'll denote this time as a big O of k, because again, we're not iterating over n the number of times. We're iterating over k, which represents the binary number of things we're iterating over. My cat Percy decided to jump on my computer. Get down, buddy. Get down. I don't know why he decided to jump up there. Well, come sit in my lap, dude. I'm not going to edit this out. Editors, leave this in. Talking to my future self. Come on, buddy. Yeah, so it's going to split the number into a binary string, and then that is what it's going to be split and iterated over with the filter right there. So it's going to be equivalent to log n, basically. So it's going to be basically the same equivalency in time. However, the space complexity on this one will be the same thing. Basically, however long and however many string characters we have to split and iterate over, so that will grow an array based on how big it is, aka O log n once again. So the space complexity is worse on this one because this split and filter will have to grow the array in place in memory somewhere, the bigger the number that we convert to binary is. So in both cases, k is the number of bits. Whenever somebody talk about k, it's the number of bits in that binary representation of n, which is why I use k in this case instead of n. And since k grows logarithmically, we can express k as big O of log n, basically. So that's like your go-to when you see binary representations. You get an integer input to grow it into a binary number. It's basically log n to do that. But the bitwise solution, as we can see, is generally more space efficient. Boom. Because it avoids creating that intermediate string and the eventual array and things like that have to come out of it in order to solve it. So yeah, there y'all have it. There is the counting set bits, Hamming weight, or population count algorithm solved with some cool new bitwise operations, some diagrams that go along with it. In terms of why it's cool, it's done a lot in error detection and correction. It's really efficient for storage. Algorithms can compress data that can use the Hamming weight to optimize how information is stored, and especially in scenarios where the occurrence of 0 or 1s is sparse or highly patterned. As you guessed, tons of use in cryptography. A lot of bit manipulation goes on in cryptography, so understanding Hamming weight can be crucial in optimizing those scenarios. You'll see it a lot in computer graphics with rendering and shading and whatnot. Encoding or decoding graphical data can involve a lot of bit manipulations where the Hamming weight can play a role. And, well, just in these kind of interview questions where they pop up and all of a sudden you can flex your knowledge and be super cool compared to the other interviewees. So there you have it. That's the ins and outs of this kind of manipulation. Hopefully a bit bit more demystified. From flipping bits to counting them, you've just leveled up your coding chops. So if you enjoyed this binary ballet and you found value in my bitwise bonanza, oh god, I gotta stop with the puns, smash that like button, do the YouTube memes, subscribe, hit the bell notification to stay tuned. Your support is what fuels both my and your journey of discovery. So if you got questions or you spark some kind of weird binary brainstorming, drop your thoughts and curiosities in the comments below. Let's keep the conversation electric. So yeah, I'll see y'all in the next video, and happy coding.